So far this week, we've focused on how computers store and manipulate integer data. And integers will also be our primary focus when we're studying CPU circuitry soon. But it's worth noting that modern CPUs also contain lots of logic for manipulating floating point data. And so we should talk briefly about how computers represent non-integer numerical data. At some point in the past, you have almost certainly encountered scientific notation, which is a way of writing very large or very small numbers in a way that doesn't take up an enormous amount of space. For example, in our normal decimal notation, this value would take at least 24 digits to write down, whereas with scientific notation, we can express it much more compactly. In scientific notation, we always have one digit before the decimal, some number of digits after the decimal, times 10 to some power. You may have encountered names for some of the parts of scientific notation, including the significand and the exponent. And the number before the decimal is standardized to be a single non-zero digit. And so normally that would be 1 through 9 or -1 through -9. The floating point standard for storing real numbers on a computer uses exactly these components, but represents them in binary. As we've seen with integers, floating point numbers can be of various sizes. Most common are 32 bits for a C float, or 64 bits for a C double, but there are certainly examples where other sizes are used, such as 16-bit floats in graphics. But I will illustrate these concepts in terms of the 32-bit floating point standard. In a C float, we have 32 bits to work with, and the first bit is used to represent the sign. We'll call that n in the expressions we'll see in a moment. The sign bit operates a bit like the first idea we mentioned for integers last time. That is, when it's 1, it indicates a negative number. When it's 0, it indicates a positive number, but it has no impact on the magnitude of the number that's represented by the remaining 31 bits. The next 8 bits are used to represent the exponent. We'll call this E in our formula. And just like scientific notation, where we can use a negative exponent to represent very small numbers, or a positive exponent to represent very large numbers, we want to allow the exponent to be either positive or negative. We could, in principle, do that by representing the exponent in 2's complement, but it turns out to be slightly easier for some circuitry purposes to represent the exponent as an offset from -127 instead. And the remaining 23 bits are the significand. You'll note that we left out the value before the decimal point, which would be part of the significand in scientific notation. The reason that we can do that is that in binary, when we're saying it has to be a single-digit number and it can't be 0, that means that this digit must always be a 1. And since we know that it is always a 1, we don't need to store it, and instead we can increase the precision of one of the other values instead. In decimal, after the point, the next digit represents the number of tenths, and then the following digit represents the number of hundredths, and so each position that we move to the right of the decimal point goes to a smaller power of 10. So in binary, the bits to the right of the point indicate the presence of a half or a quarter or an eighth, and so on, each representing a successive power of 2. To help make this clearer, let's go through an example of converting a 32-bit floating point value to decimal. For this 32-bit floating point value, we have 1 bit for the sign, then 8 bits for the exponent, and then 23 bits for the significand. Since our sign bit is a 1, we know that this is a negative number. The exponent we can read as an unsigned binary number. We have 1 plus 2 plus 128. So we get 131. And then we subtract 127. So we get a value of 4 for the exponent. Then for the significand, we have no halves, a quarter, an eighth, no sixteenths, and a 32nd. So now we can put all of the pieces together. So we have a minus sign out front. Then we have always on the significand the implied 1 point. So we have 1 and 13/32. And then we multiply by 2 to the power of the exponent. 2 to the 4th is 16, so this product becomes 16 and 13 halves. And our improper fraction is equal to 6.5, so this is equal to negative 22.5. And so we can write down the general formula for converting from a 32-bit float to a decimal value. And this formula is expressed in terms of the sign n, the exponent e, and the significand s. We can compute minus 1 to the n, so minus 1 to the 0 would give us 1, and minus 1 to the 1 would give us negative 1, so that will always give us our sign, times 1 point the significand, times 2 to the power of our exponent minus 127. And so to get a decimal value, we would need to convert the fraction s and the integer e into decimal values, and then we could evaluate this formula.